Well, hello, fellow peasants. It's me, Maiden Mayhem, causing chaos and mass hysteria, keeping you informed about scientific research, especially in the context of infectious diseases. Well, at least that's TikTok's opinion of me. A few days ago, I did a video informing you that they identified the superantigen. Apparently, TikTok thought that was great news. For once in my TikTok career, my content wasn't completely throttled. Well, with a name like Super, it's gotta be good, right? Anyway, in the comments, there were a lot of questions about what is a superantigen. And while I told everybody that I would make a video the next day, after that, TikTok was not happy with the girl for getting one over on them. So they participated in some retaliatory practices, if you know what I mean. I'm hoping they'll move past it, but you never know. But if you're ready, let's hop on this learning express. Toot toot! Well, first things first, what is an antigen? Simplified, it's a molecule or a particle that triggers an immune response. It's extremely diverse and specific to each person. For example, there are blood antigens that designate your blood type. For example, a person with type A blood has A antigens on their red blood cells. A person with type B blood has B antigens on their red blood cells. A person with AB blood has A and B antigens, while a person with type O blood has none of the A or B antigens. This is why blood matching exists. Because if a person with type O blood is given blood from a patient with type A, then their body is going to recognize A antigen shouldn't be there and destroy those red blood cells. Other antigens can cause allergic reactions in some people, like bee venom. Also, antigens from pathogens like viruses. And in the context you're likely most familiar with antigens is in the context of vaccines, where we train our immune system to target a part of the virus like the spike protein to destroy it. The antigen can be recognized in the bloodstream by antibodies, or in a viral infection where the virus enters a cell. Fragments of it can be taken to the cell surface, where the antigen is then presented to T cells on either the MHC1 molecule or the MHC2 molecule, therefore activating T cells to begin destroying compromised cells. Conventional antigen will only activate 0.0001% to 0.001% of all of our T cells at once. Because remember, one of the jobs of the T cells is to destroy our own cells, and we don't really want to do that. It's a lot of work to make a cell. We don't want to destroy them for no reason. T cells are kept on about as short of a leash as I am on this app. Kidding. But seriously, T cells can be quite destructive. They can destroy cells and release cytokines. And while T cells are originally formed in the bone marrow, they are trained in our thymus and are finite in number. We are born with most of the naive T cells we'll ever have in our life. Our thymus, where they're trained, stops growing at puberty and in adulthood begins to atrophy or shrink. Naive T cell production is nearly non-existent in adulthood. When naive T cells are presented with a specific antigen, they will mature to specifically target that one antigen. And they are referred to as mature T cells. They were given their target antigen, and they understood the assignment, so they matured to target it. So throughout life, our naive T cell pool dwindles, but granting us a diverse, mature T cell repertoire. So often, if you've already been exposed to something, your body isn't going to want to use the naive T cell pool. Instead, it'll make copies of, or clonally expand, a mature T cell that specifically targets that one antigen, preserving your naive T cells for threats you haven't been exposed to yet, while boosting the number of T cells specific to that antigen during that infection. There's a limit to that too. As I said, in a typical infection with a conventional antigen, the maximum amount of T cells that will be activated is 0.001%, who may go through 1 or 2 cycles of cell division. Now, the normal activation of a specific T cell will require a processed antigen on the MHC2 complex with the T cell receptor. A superantigen can activate any T cell without even presenting an antigen. It does this by cross-linking the MHC2 receptor with the T cell receptor of any T cell. Because it's not being specific with which T cells it's activating, often you will see a massive cytokine release. Superantigens can activate up to 30% of our T cells, including the naive T cell pool, while simultaneously inducing mature T cells to go through several cycles of cell division, thereby exhausting them. The superantigens are a big deal. They can cause our naive T cells to become depleted. It can also cause those mature or specialized CD4, CD8 T cells proliferate and produce a cytokine storm that drives those mature T cells into a state of exhaustion, essentially. If you have depletion of your naive T cells and exhaustion of your mature T cells, that could potentially allow a pathogen to evade the immune system. Superantigens can also cause autoimmunity. It can also impair post-vaccination memory T cell recall, even to unrelated antigens. Also, SAG-like proteins that are implicated in causing thrombosis or clotting or bleeding issues, primarily through platelet activation. We have known about superantigens for a while. In fact, you are probably familiar with them without recognizing that you're familiar with them, at least their effects. Examples of superantigens are staphylococcal enterotoxins, staphylococcal toxic shock toxin, streptococcal pyrogenic exotoxins, and mouse mammary tumor virus, a retrovirus, which causes breast cancer in mice. Something you've probably heard a lot of in the news is Staphylococcus aureus. That bacteria is known to secrete multiple superantigens, referred to as staphylococcal enterotoxins, and there's SEA through U, there's several types. SEA, or staphylococcal enterotoxin A, is primarily responsible for food poisoning. SEB, staphylococcal enterotoxin B, is considered to be one of the most important toxins in bioterrorism. Some of the other diseases caused by superantigens are toxic shock syndrome, streptococcal disease, autoimmune diseases, Kawasaki syndrome, scarlet fever, necrotizing pneumonia, acute rheumatic fever, eczema, and scalded skin syndrome. Prolonged superantigen exposure is thought to either result in exhaustion, deletion of T cells, or autoimmunity. While treatment typically involves eliminating the source of the superantigen, stimulating B-cell production of antibiotics, use of immunoglobulin pools, immunosuppressants, synthetic antibodies and peptides, and corticosteroids. Unfortunately, for the last several decades, we've tried to produce vaccines against these superantigens without success. Now, in the study that identified the superantigen or the superantigen-like protein on the SARS-CoV-2 virus, identified it on the S2 region of the spike. This region was termed P3 or P3b and other variants of SARS-CoV-2. This paper identified that P3 and P3b had 67% similarity with Staphylococcus enterotoxins B and H. Now, this video is already getting pretty long, but if you want to know more information about this paper specifically, and also with the context of some of the other things that we know about the SARS-CoV-2 virus, please let me know in the comments. Anyway, I hope that helped.